time we stopped at with mean value theorem. Let us look at some important results that come out as direct consequences of mean value theorem. So corollary 1, if f is continuous, well, yeah, let me go with, yeah, so we don't need that. I think if f is defined on an interval AB, on an interval, doesn't matter if it's closed or open, and f prime of x is equal to 0, for all x in the interval, then f is constant on the interval. Then f is constant on the interval. Proof? Okay. First, there needs to be a small observation that is made. Like, yes, you know that, oh, if the derivative is 0, you have seen this before, that if the derivative is 0, the function is a constant. But you might be tempted to say, hey, if I look at the function which is something like this, right, which has a jump, then the derivative is 0 here, the derivative is 0 here, derivative is 0 everywhere. Why is this function not a constant? It's constant on parts. And the problem is here, f prime of x is not defined on this point, not defined at this point, right? And so the hidden assumption that we are making, not exactly assumption, but hidden statement that is included in the corollary is f prime x is equal to 0 for all x in the interval implies that f of x is actually differentiable and therefore also continuous, on the interval. Okay, so that's a hidden assumption that is being made. Well, I mean, not explicitly said, but it is being told to you. Okay, so now let us get to the proof. Suppose there are 2 points. Suppose a comma b belong to the interval I. So I'm going to call my interval I. Okay, let me define interval I on the interval I, and f is constant on the interval I, right? So I'm not talking about the unit interval, but I'm just saying that, any interval, I want to give it a name. I don't want to keep referring it to as the interval. So suppose there are a and b in I such that f of a is not equal to f of b. Okay, suppose they're different. But then that means by mean value theorem, I can take, there exists, by mean value theorem, there exists x on the interval in a to b, which is a subset of the interval I, such that f prime of x is equal to f of b minus f of a over b minus a. Okay, but since x is in the interval I, f prime of x is equal to 0. So therefore 0 is equal to f of b minus f of a over b minus a. Therefore f of b minus f of a is equal to 0. Therefore f of b is equal to f of a. And that's a contradiction, right? But that is also showing that whatever happens, if you take two different points a and b, it has to be the same. Okay, that's the first corollary. Corollary 2. Corollary 2. If f and g are defined on the same interval, if f and g are defined on the same interval I, and the derivatives are equal everywhere, f prime of x is equal to g prime of x for every x in I. For every x in I, then I have that they have to differ by a constant. Then f of x, well, f is equal to g plus c for some constant c, for some number c. There is some number such that f is equal to g plus c. It has to be the same number everywhere. Proof? Well, let us look at f minus g prime of x. This is equal to f prime of x minus g prime of x, which is equal to 0 for every x in I, right? Therefore, f minus g by previous corollary is a constant, right? Constant function. Suppose it is a constant function, say f minus g of x is equal to c. Therefore, f is equal to g plus c as required, right? That's the second corollary. And before the third corollary, let us do some review of some definitions that we had discussed before. But in case you forgot about them, I'm going to write them again. F is increasing on an interval I, on an interval I, if for every a comma b in I, a smaller than b implies f of a smaller than f of b, right? Similarly, f is decreasing on an interval I if for every a comma b in I, a smaller than b implies f of a this time is greater than f of b. Great, I have my definitions of increasing and decreasing. Then I can state my corollary 3. If f prime of x is greater than 0 for all x in an interval, if f prime of x is greater than 0 for every x in, well, I shouldn't write that, greater than 0 for all x in an interval I, then f is increasing. What is this? Then f is increasing on the interval I. Similarly, if f prime of x is smaller than 0 for every x in I, then f is decreasing on the interval I. Okay? Proof. I'm only going to do the proof for increasing. Proof for decreasing is similar. I will leave you guys to do it. Suppose we are going to do this by contradiction. Suppose there exists a comma b in I such that a is smaller than b and f of a is greater than f of b. That would mean the function is not increasing, right? There are some a and b where the increasingness of f is reversed. It's not holding true. Then f of a minus f of b minus f of a over b minus a is smaller than 0, right? Because f of b is smaller than f of a, and b is greater than a. So the top is negative, bottom is positive. That means the whole thing is negative, right? But therefore, there exists x in the interval a to b, which is a subset of I, such that f prime of x is equal to f of b minus f of a over b minus a is smaller than 0. Contradicting f prime of x is greater than 0 for every x in I. Right? Our initial assumption was that the derivative is positive for everything in my interval I. These a and b are giving me a counterexample to those, which should not happen, and that means f of a should have indeed been less than f of b. I will leave the proof of the decreasing case to you and stop this